Here slopes also very much important. For zero order only K, for first order K by 2.303. Some of the reactions will behave like first order reaction but does not follow the overall factors of first order reaction. Those kind of reactions will be considered as pseudo first order reaction. Next problem, 60% of first order reaction was completed in 60 minutes. What was it? Half life completed. This is also first order reaction, but we have to consider the half-life time. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now I am going to start session 3 from the chapter Chemical Kinetics. In the last session, we have discussed about order of a reaction, types of reaction, difference between order and molecularity, and units of rate constant with its numericals. So these are the concepts which we have already discussed in previous session, and we'll continue that session by using the content with integrated rate equation. In that we'll derive zero order reaction and first order reaction and significance of first order rate equation and rate constant for first order gas phase reaction. As I told earlier, these are the overall derivation part and which is very much important for your examination purpose. Integrated rate equation. The differential rate equation gives the relationship between the instantaneous rate and rate law. But it is difficult to find out experimentally that instantaneous rate by using the given data. So they are using integrated rate equations. In that, we'll first derive the zero order reaction. Zero order reaction is the rate, it's the reaction in which the rate of a reaction is completely independent of molar concentration of reactant. So consider a reaction, that is reactant giving product. Rate, we know how to write the rate of that concentration of reactant at unit time. So K is nothing but rate constant into concentration of reactant, but the power is 0 because it is a zero order reaction. If any constant with the power 0 means it will show unity, that is 1. So rate equal to minus into concentration of reactant at unit time. So K into 1, because it is having power 0, it will represented by 1. And dr into minus K dt. Okay. And integrating both the sides, after rearranging the equation, we will get dr equal to minus K dt. Integrating both the sides, on the rearranging, after that integrating both the sides, r into minus kt plus I. What is I? I is the constant of integration. Okay, after this integration, this I will be introduced, that I is the constant of integration or integration constant. At time equal to 0, the concentration of the reactant, concentration of R, that is reactant, to 0, where R naught is the initial concentration of the reactant. This is initial concentration of the reactant, this is molar concentration of the reactant. That will be same now or equal by substituting the equation 1. See here, this is equation 1. For that, we have to substitute R naught equal to minus K into 0 plus 1 plus I. R naught equal to I, because minus K into 0, 0, 0 plus I, only I. Substituting the value of I in the equation 1. Minus KT plus initial concentration, because I is nothing but initial concentration. Further simplifying equation 2 means my K we are taking to left hand side, this minus will become positive, equal to initial concentration minus molar concentration divided by T. After all simplifying or rearranging, we will get K into initial concentration minus concentration divided by T. Okay. With the equation of straight line, see here, when we put the graph or plot the graph concentration of reactant by time, it will be arranged in straight line having the slope K. Okay. This is about zero order reaction. So for the zero order reaction, this will be the equation. That equation is very much important, and this straight line will show the y equal to mx plus c. Next is first order reaction. First order reaction means it is a reaction which the rate is directly proportional to the reactant, the molar concentration of the reactant. If we consider one general reaction, reactant giving product, we know how to rate of a reaction, concentration of reactant by time, and rate will be K into R. Nothing is there means we know that is 1 is present, 1 means first order. So d into R by dt, that is concentration of reactant by at time, K into dt will be present. Integrating on both the side, while we are integrating like this, integrating on the both the side, ln R equal to minus KT plus I. We know what is I. I is the integration constant. At time equal to 0, R, that is concentration, will be equivalent to initial concentration. Here also R naught is the initial concentration of the reactant. Substituting in equation 1, ln R naught equal to minus K into 0 plus I. Here also ln R naught will be equivalent to I. Substituting the value I in the equation 1. In the equation 1, what will happen? Ln R equal to minus K into T plus ln R naught, because I will be equivalent to ln R naught. KT into ln R naught minus ln R. This KT we have taken to left hand side. This ln R naught minus ln R. When we have to only find out K, that is rate constant, we have to take left hand side completely. Then T will become 1 by T ln R naught divided by ln R. Okay, K equal to 2.303, because ln we are converting into log. So 2.303 divided by T into log into initial concentration by concentration. This is the final equation to find out the integrated rate equation for first order reaction. These equations are very much important to find out or to implement in the problems also. Next, significance of first order reaction. Consider ln R equal to minus KT plus ln R naught. Comparing equation with y equal to mx plus c, if we plot ln R, concentration of reactant to or versus time, if we plot, it will also get straight line with having minus k slope. It is equal to ln of, that is concentration of initial concentration. The first order rate equation means K equal to 2.303 divided by T into log initial concentration by concentration. If we keep left hand side, KT by 2.303. Here slope will be K by 2.303 will be present. If we plot between log of concentration initial, that overall concentration divided by T, will get slope K by 2.303. Here slopes also very much important. For zero order only K, for first order K by 2.303. At time T1 from equation, ln R naught will equal to minus KT1 plus ln R naught from the equation 1. Wherever it was 0, it has become 1, because T equal to not 0, it is T equal to 1. At time 2, same thing, R2 and minus K2, KT2 plus ln R naught. And concentration of reactant 1 and 2 are the concentration of the reactants at time T1 and T2 respectively. Substituting or subtracting equation 2 from 1, this equation from and that equation, ln R1 minus ln R2 equal to minus KT1 of minus KT2, because we are subtracting from equation 2 to equation 1. What will become? Ln R1 by R2, that is concentration of 1 and 2, and K into T2 minus T1. K equal to 1 by T2 minus T1 into ln of concentration of R1 by R2. K equal to 2.303 divided by T2 minus T1 log of R1 by R2. This is another equation when time equal to 1. Okay. Rate constant for first order gas phase reaction. Here A is giving rise to B and B plus C. Here we are considering gas phase reaction. Let us consider a typical first order gas phase reaction. Let Pi be the initial pressure of A and Pt the total pressure at time t. Pi be the initial pressure, Pt be the total pressure of at time t. Integrated rate equation for such reaction can be derived as Pt equal to Pa plus Pb plus Pc. Pa, Pb, Pc are partial pressures of A, B and C respectively. If X at B, the decrease in pressure of A at time t, 1 mole each of B and C being formed, the increase in pressure of B and C will also be X atm at atmospheric pressure at each. Okay, this is the general introduction part. Once again, we are considering one gas phase reaction. A is giving rise to B plus C. Here Pi be the initial pressure and Pt be the total pressure at time given. Pa, Pb, Pc are the total pressures and respective pressures of A, B and C. For the given reaction, we are considering this is initial concentration and at 0 atmospheric pressure and both are 0. Here Pi minus X, because here X atmospheric pressure is given. At time equal to 0, all are the given conditions. At time equal to T, where Pi is the initial pressure and time T equal to 0. Pt equal to Pi minus X plus X plus X. So what will happen? Pi plus X. X equal to Pt minus Pi. Total pressure minus initial pressure, where Pi equal to P1 minus X equal to Pi minus Pt minus Pi. Okay, 2 Pi minus Pt. K equal to 2.303 divided by T into log of Pi minus divided by Pa. So 2.303 divided by T into log of Pi by 2 Pi minus Pt. What we have seen in the significance of first order reaction, that equation has been implemented here. Okay, this is about first order gas phase reaction. Next, half-life of a reaction. The half-life of a reaction is the time in which the concentration of reactant is reduced to 1/2 of its initial concentration. Half-life of a concentration means, half-life of a reaction means, whatever the initial concentration of a reaction is there, it will be reduced to 1/2 of the reaction. So it will be called it as half-life of reaction. It will be represented by T-half. So half-life of zero order reaction. For a zero order reaction, rate constant is given equation. For zero order, we know initial concentration of reactant minus concentration of reactant by T. So if we implement here, T-half equal to R, concentration of R equal to minus half into R naught. The rate constant at T-half become initial concentration minus half into initial concentration by T-half. So T-half, if we want to calculate, we have to take into left hand side. 2K will become here and initial concentration. It is clear that T-half for a zero order reaction is directly proportional to the initial concentration of the reactant and inversely proportional to the rate constant. See here, T-half is directly proportional to the initial concentration, inversely proportional to the rate constant. For half-life for first order reaction, K equal to 2.303 divided by T into log of initial concentration by final concentration. At T-half, R equal to initial by final. So the above equation becomes K equal to 2.303 divided by T-half into log R naught by R by 2. T-half equal to 2.303 by K. We can interchange here into log 2. T-half equal to 2.303 by K into 0.301 because log 2 will be 0.301. So what will happen? T-half equal to 2.693 after multiplication this one divided by K. It can be seen that for a first order reaction, half-life period is constant. That is, it is independent of initial concentration of reacting species. For a zero order reaction, T-half is directly proportional to initial concentration. For first order reaction, T-half is independent. Okay. Next, pseudo first order reaction. Pseudo means some false or not completely happened truly. Chemical reactions which are not first order but behave as first order reaction under suitable conditions are called pseudo first order reaction. Some of the reactions will behave like first order reaction but does not follow the overall factors of first order reaction. Those kind of reactions will be considered as pseudo first order reaction. A reaction which involves two or more molecules of reactants but the order is 1 called pseudo first order reaction. It can be stated as like this also. Or more molecules are present but order showing is 1. Example, acid hydrolysis of methyl acetate. Here also rate is concentration will be of water is 0 and ethyl acetate is having 1 but order is 1. The reason being water is present in a large excess and its concentration remains constant throughout the course of the reaction. Since throughout the course of a reaction water will not be changed, it will be constant, so power will not change and it will remain as first order reaction. Inversion of sucrose is also same thing. It is the pseudo first order reaction. And overall view of zero order and first order reaction. Rate law, rate in the first order, in the zero order, rate equal to K into concentration of reactant. Units for K, mole per liter per second, this is only per second. Half life, initial concentration by 2K, this is 0.693 by K. If integrated rate law equations, straight line form, A into concentration of A into minus KT plus initial concentration, here ln A equal to minus KT plus ln initial into concentration. Plots for straight line, R versus T, that is initial concentration versus T, this is ln R versus T. Slope y-intercept minus K or initial concentration, here minus K or ln of initial concentration. This is the overall view of zero order reaction and first order reaction with respect to these conditions. Next we will see some of the numericals. Calculate the time in seconds for which decomposition of nitrogen pentoxide, which follows first order kinetics when concentration is N2O5 is dropped, that is nitrogen pentoxide is dropped from 0.1 molar to 0.01 molar. K equal to, that is rate constant equal to 6.22 into 10 to the power of minus 4 per second. It is under first order kinetics. So what is the equation? T equal to 2.303 divided by K into log of initial concentration by concentration, okay, of reactant. T equal to 2.303. We have to calculate T only. So let it be equation like this only. T equal to 2.303. What is K? 6.22 into 10 to the power of minus 4 into log 10. Okay, into log 10, 0.1 divided by 0.01 because it is dropping to initial concentration to final concentration. 2.303 divided by 6.22 into 10 to the power of minus 4 log n, that is 10 equal to 3.7 into 10 to the power of 3 second. After all simplification, first you have to simplify here and you have to calculate to log 10 and then 2.303 by this much. After all calculation, it will become 3.7 into 10 to the power of 3 seconds. Next problem, 60% of first order reaction was completed in 60 minutes. What was it? Half life completed. This is also first order reaction, but we have to consider the half life time. For first order reaction, K equal to 2.303 by T into log 10 by initial by final. R equal to 100 minus 60 because they have given 60 minutes. So overall minus 100, in the percentage wise 100 only total. So 100 minus 60, 40%. 2.303 by 60 into log 10 by 100 minus 40. This was the final. And 100 minus 100 by 40, how much? 2.5. And K equal to minus 1.527 into 10 to the power of minus 2 per minute. This is about K. Okay, but we have to find out half life of a first order reaction. So half life log half into K equal to, that is T half equal to 0.693 by K. So 0.693 divided by 1.527 into 10 to the power of minus 2 per minute. It will become 45.38 minutes. This is how the half life of a first order reaction you have to find out. If they have not given K, you have to first use the integrated rate equation of first order reaction, find out the K, later implement for the half life of a reaction. Next, the decomposition of ethene to methyl radicals is a first order reaction. with a rate constant of 5.36 into 10 to the power of minus 4 per second at 700 degrees Celsius. Calculate the half-life of a reaction. They have given everything here. So we can directly go for half-life of first order 0.693 by K. This is constant, and 5.36 into 10 to the power of minus 2 per second. They have given here the rate constant. So directly simplify 1.29 into 10 to the power of 3 per second by 60, because we have 2 minutes. We have to conduct in minutes. So by 60 it will form to 21.5 minutes. These are the numericals and also integrated equations of zero order and first order gas phase reaction. In the next session, we will discuss about temperature dependence of the rate of a reaction, Arrhenius equation, activation energy, qualitative increase in reaction rate with temperature, and some of the numericals. This is the very important session which is upcoming. Then I hope you have completely understood whatever I have taught today. We'll meet in the next session. Thank you.